thanks a lot for the introduction and for the invitation to talk at this nice conference. Unfortunately, I cannot be there in person, but I believe that my collaborators are there in the audience. So if after the talk, just any of you have any questions, I encourage you to go and talk to them, and I'm sure that they will be happy to have discussions about this. So I will be talking about two papers that we put out earlier this summer in collaboration with Andis Vesco, which is a from Qubit postdoc at University College London, Andrea Russo, who is a PhD student there, and Zach Wheeler-Davis, who was a former PhD student and now is a postdoc at Perimeter Institute. So I'm gonna be telling you about holographic complexity, and more specifically about reformulation of one of the proposals of holographic complexity, the so-called complexity equals volume proposal, in terms of Lorentzian threads. This is analogous to the reformulation of the Ryu and Takayanagi prescription in terms of Riemannian bit threads, which was put forward a couple of years ago by Friedman and Hedrick. So, okay. This is more or less the outline of my talk. I'm gonna give a very brief motivation about our work. Then I'm gonna just move to the reformulation of complexity equals volume in terms of threads. I'm gonna tell you about the prescription and the properties, the interpretation, and then I'm gonna show you a nice application of this. That is a connection of between the first law of complexity with the bulk Einstein's equations. Then I will finish up with some comments about the CV proposal and why we think that there should be a more general prescription for holographic complexity. Time permitting, I will also flash some of the ideas that we are still thinking about and that we think are interesting to explore. So let me start with the motivation. All this holographic complexity was first discussed a couple of years ago. Since Susskind told us that, okay, entanglement entropy is very useful in the context of holography, but is certainly not enough to describe all aspects of gravitation of bulk physics. In particular, it's not enough to describe the late-time growth of the wormhole inside a two-sided black hole. And he was thinking about what possible CFT quantity or observable is useful to characterize this growth. So a natural candidate that he came up with is a quantum or computational complexity. So in a few words, this quantity is defined as follows. So first, you defined a reference state, and then you defined a target state. And then upon selecting a set of elementary gates or operations that you are allowed to act with, then you count the minimal number of operations that take you from the reference to the target state upon some level of accuracy. So there are indeed, it is known that in quantum information, it's known that even though entanglement can thermalize in a scale that is polynomial with the number of degrees of freedom, the complexity can evolve over a longer time scale, over a scale that is exponential in the number of degrees of freedom. So apparently it's a good candidate. There are, of course, two main candidates for what the dual of this quantity is in the bulk. I said two main because right now there are many more other quantities that are possible duals to this CFT quantity. But I'm just gonna focus on the main two ones. The first one is the complexity equals volume proposal, which gives complexity as the maximal volume of a slice that is anchored at some time slice in the boundary. Okay, so this is the first proposal. The second proposal is instead given by now the gravitational action evaluated at a Wheeler-DeWitt patch, again anchored at this boundary time slice. Okay, so these two proposals share some of the qualitative properties. So they both capture the late time growth of the wormhole. They both saturate the so-called Lois bound, and they reproduce the an effect that is known as the switchback effect. That is when you have when you perturb the black hole with say shockwaves. However, there are a number of features that are not well understood, or they are mysterious. For example, it is not clear what is the role of the reference state in both proposals. It is not clear what is the set of gates that we need to specify from the bulk perspective. It is not clear what the tolerance is. And more importantly, these are just conjectures, but there is no first principle derivation from using the tools of holography. So these proposals are not in equal footing as, for example, entanglement entropy, in the sense that we don't have a first principle derivation. So in this talk, I'm going to be telling you about a reformulation of one of the two proposals, the CV. And with this reformulation, we basically learn we clarify at least some of these points that are not so clear. Okay, so before I tell you about this reformulation, let me just in one slide summarize the proposal by Friedman and Hedrick of how it is possible to reformulate the RT prescription using bit threads. So in this equation, in the left-hand side, we have the formula that we all know. This is the RT formula. With this formula, we can compute entanglement entropy in terms of the areas of certain surfaces in the bulk. And at the right-hand side of this equation is the reformulation. So in this new formulation, we don't need to talk about surfaces in the bulk. Instead, we introduce a new object that is a flow. A flow is a vector field that satisfies a number of properties. So these vector fields are divergenceless, and they are norm-bounded by the Planck length. And basically, the equivalence relates the minimal area of these surfaces by the maximum flux through the corresponding region in the boundary. So there is a proof of this equivalence. It follows from the continuous max flow min cut theorem. And this can be proved more rigorously using techniques of convex optimization. It was done in a follow-up paper by Hedrick and Huveni. What is insightful about this interpretation is that it offers a more fine-grained description of what this formula is telling us. So in particular, one of the properties about these flows is that, as I said, they are divergenceless. So this means that there are no sources in the bulk, rather the integral lines, which we call threads, they must start and end at the boundary, right? So if you think of the discrete version of this problem, then this max flow is counting the maximum number of threads that connect the points or degrees of freedom inside the region of interest with the complement. So in other words, they are counting the number of bell pairs that you can distill from the state. So this is nice because this fits well with the intuition that we have from quantum information. And it has helped us clarify some aspects of entanglement that were not well understood. For example, that it had helped us to understand what derived quantities such as mutual information and entanglement of purification, what are they computing in the bulk, and to clarify what is the interpretation of inequalities such as the monogamy of mutual information or even higher party inequalities. So this is all nice, and but now I'm here to tell you about holographic complexity. So based on the analogy of the complexity equals volume proposal and the RT prescription, then it is natural to conjecture that this proposal must have a flow-based prescription. And indeed, there is an analogous version of the max flow mean cut theorem that is a Riemannian. There is an analogous version that is Lorentzian, that is the so-called mean flow max cut theorem that was also proved by Hedrick and Huveni in their paper. And one can use that theorem to reformulate this conjecture in terms of flows, as is given in this equation. I should point out here that this reformulation was already proposed in their paper by Hedrick and Huveni, but our job was to push it forward and to explore the properties and see what is the interpretation and so on. So there are a couple of distinctions between this and the standard bit threads prescription. The most obvious is that here we are dealing with a Lorentzian manifold instead of a Riemannian one. Here we have a flux minimization rather than a maximization. And these vector fields now are time-like instead of space-like. And finally, the bound here is in the opposite direction. So we have a minimal bound. So this is kind of a visualization of how one of these flows look like. Very importantly is that for this theorem to work, it is very important that the manifold is to be compact. So just to be more precise, what we need to do is to start with a Lorentzian manifold and glue Euclidean portions both in the infinite past and in the infinite future. Once we do that, is that we can make use of this theorem. Now, the fact that we need to add these Euclidean portions, it reminds us of another topic that is commonly discussed in gravity, that is a topic of state preparation. And this is very nice because it makes, in some sense, evident the role of the reference state. So what we normally say is that we specify boundary conditions in this lower part of the Euclidean hemisphere, and we specify some sources. Then Einstein's equations will tell you what is the state that is given here as an initial data. Another way to state the same problem is that you can also give the state both in the infinite past in this Euclidean section, and you can also specify the state on this disk, and then you can ask the question of what sources do you need to turn on, such that the evolution, the dynamical evolution, will bring you one state to the other. Right, so that is very nice. In particular, we can see that if the reference and target states are the same, then we don't need to turn on any sources. And then what happens is that you can collapse this Euclidean part of the manifold to a point, and then the resulting volume is zero. Another nice interpretation is that now the threads that are the integral lines of these vector fields, these are word lines. So instead of connecting degrees of freedom that live on the same state, now what the role is to transport individual degrees of freedom, evolve them in time. And it's tempting to interpret these threads as gates in such a way that in the discrete version, this minimal flux is actually computing the minimal number of threads or gates that bring me from the reference state that is specified in this Euclidean part to the target state that is specified on this disk. We can also say something about the tolerance that is actually in the discrete version. It is equivalent to the volume, that the transverse volume that these threads will have. And this is essentially the minimal unit of volume that we can resolve with this prescription. There are a number of properties that follow from the one that is very important is nesting. That refers to a situation in which we have two nested surfaces. And by nested, in this case, we mean nested in time. So here we have two surfaces, A and AB. And if we do that, then the nesting theorem tells us that there should be at least a flow that simultaneously minimizes the flux both through A and through AB. Okay, so based on these nested situations, then we can come up with more exotic optimizations, such that instead of only having a reference and a target state, we can also now introduce an intermediate state. So we can propose this new quantity that we call conditional complexity, that is the complexity of a state, but subject that the optimization has gone through an intermediate state. So, and based on this flow prescription, we can come up with a natural definition for this quantity. Another nice thing is a connection. Like, so if we let these nested surfaces to be infinitesimally far apart in time, then through what is called as momentum volume complexity correspondence, we can come up with a natural candidate for one of these flows that do the simultaneous minimization. So this natural flows is in terms of the stress tensor. This n is a normal vector, and this theta is an infalling vector that is parallel to the surface sigma. More importantly, if you repeat this exercise with 3 nested surfaces and let the time to go to 0, then you arrive to this well-known equation that relates the second derivative of complexity with the first derivative of momentum. So in a sense, this is really nice. This is why Susskind proposed that the origins of Newton's law of gravitation have an origin in complexity. There is another nice property that we can derive very easily in terms of flow, but I'm probably not going to have time to talk about it, is the superadditivity of subregion complexity. Subregion complexity is a derived quantity that arises from dividing your boundary Cauchy slice into two, for example, 2 subsets, and then you ask what is the complexity of each of the subsets. So there is a property that is called subadditivity that is obeyed for CV, and we can similarly derive it using the language of flows. Now let me move to the interpretation. In order to understand this, it's worth to remind you that we can discretize slices in an ADS space in terms of a tensor network. So in order to do that, so I write in here the wave function. And first, what you need to do is to express the basis states as a product of local state vectors. Then what a tensor network does is to provide an ansatz for these amplitudes. And depending on the ansatz, you can have different structures, can have different kind of tensors, different contractions, and so on. Here, I'm just providing a very simple illustration of one of the simplest one that is called MERA, or multi-entanglement renormalization ansatz. This simple network is very useful for systems with a conformal symmetry, and therefore very useful in holography. It has only 2 types of tensors, and it has a layer structure such that in each layer you only have 1 type of tensor. So you have the isometries that they basically combine a subset of the degrees of freedom, and can be regarded as a coarse graining, or yeah. So these are physical degrees of freedom, but if we only construct a network with this type of tensors, they are not enough to describe some features of the state. So instead, we need to add a second type of tensors that are called disentanglers. that they are added in intermediate layers. And they do not represent physical degrees of freedom, but rather they represent unitary operations that evolve the system at one of the layers to a less entangled state in the next layer. And in the continuous limit, of course, these entanglers are the ones that implement the evolution in the holographic or radial direction. Now, what I want to emphasize here is that the CV proposal was first indeed inspired by TensorNet. In particular, the idea is that the tensors, the physical tensors in a given network, they occupy some finite volume. And the idea is that the complexity is given by the number of tensors in the network. Now, given that we also have a discrete version of our flow reformulation, then it's natural to combine the two. So we interpret now threads as gates or gatelines. This was some terminology that was introduced by Matt and Veronica. And in a way that now we are computing complexity by either counting the number of gates or the number of physical tensor in the network, discretizing the slice, right? So now we are gonna, these threads are gonna pierce through the physical tensors in the network, and we're gonna attach unitary operations or unitary gates to each of the threads, in such a way that they act very similar to what I told you about in the previous slides as the disentanglers. Now they are gonna generate the evolution in Euclidean time. Now, at this point, it's worth mentioning that this reformulation suggests that the gates are mostly commuting in the sense that they don't mix degrees of freedom. This might be so first, this is equivalent to the statement that Riemannian bit threads suggest that the state can be mostly constructed from bipartite entanglement. So this is in general not true, but there are ways to go around it and to generalize the bit thread prescription to account for multipartite entanglement. So I'm going to come back to this in the outlook if I have time, but at this point, I just want to mention that this suggests this property. Finally, let me just mention that okay, this picture of gates, this is of course in the Euclidean portions of the manifold, but upon analytic continuation, then it's natural to propose that are these unitaries the ones that generate the evolution in real time, and in such a way that time emerges naturally from these constructions. Now let me move to one of the applications. That is the connection with Einstein's equations. In order to do that, it was natural to us to reformulate this formalism in terms of differential forms. So we know that vector fields map to d-1 differential forms, and therefore we can likewise reformulate the flux minimization in terms of a flow in terms of differential forms. Next, we develop a notion of perturbative Lorentzian threads or flows, and for that, then we imagine having in a state that is slightly perturbed over a reference state, in such a way that the flow also develops a correction that is linear or higher order in the perturbation. Using covariant phase space techniques, then we realized that there is a natural candidate for this perturbed form that is actually given by the bulk symplectic current. The bulk symplectic current is defined in this way, where this theta is the bulk symplectic potential that arises in arbitrary variations of the gravitational Lagrangian. So there is the first term that is the standard one where you get the gravitational equations, and the second term that is the so-called bulk symplectic potential. So our observation is that the bulk symplectic current provides actually a solution at linear order to the minimization problem. In addition, we made this connection. So we noticed that this is not the first time that this symplectic current has been discussed in the context of complexity. There is this set of papers by these authors. And it's nice that they observe that when the sources are deformed by the so-called New York transformation, then the bulk symplectic current provides us with a natural definition for a first law of complexity. So the bulk symplectic potential evaluated at the boundary of the Euclidean part of the manifold gives you the change in complexity, and the bulk symplectic current integrated over the maximal slice gives you the change in the volume. The key point here is that this form is closed for on-shell perturbations. So the exterior derivative is proportional to the linearized Einstein's equations. So for any on-shell background that we have, then we have that this form is closed. Then we can use Stokes' theorem to perform this volume integral now over one of the Euclidean portions of the manifold. And we know that by Stokes' theorem that this is equivalent to this difference, change in complexity minus change in volume. So this is nice because at the right-hand side, we have this is zero if the state satisfies the first law of complexity. But in the left-hand side, we have Einstein's equations in an integrated form. So the idea here is very analogous to what is done in the context of entanglement entropy, is that we can consider now the first law, we can impose that the first law applies not only for the state on the slice sigma, but that is also valid for arbitrary Lorentzian initial data on other slices sigma prime. So to do that, then we deform the integration contour to allow for a little bit of Lorentzian evolution that is represented by this part of the cylinder. And then we can just boost our slice sigma to or add a time translation and so on. And when we transform back to Euclidean signature, then these boosted slices, they correspond to other sections of the Euclidean ball, right? So the idea here is that now we demand that the first law is satisfied for all these possible sections, and with that we were able to show that actually all the linearized Einstein's equations follow from imposing the first law for all these initial data. So in a sense, this is nice. This is a nice result that we can see that Einstein's equations now emerge also from complexity, specifically from complexity equals volume proposal. Let me just now share some final thoughts on CV. We were wondering if the optimal network defined on the maximal volume slice is sufficient to characterize complexity for arbitrary states. And upon thinking on this problem, we think that we arrived to an argument to say that it is not, it is not sufficient. So the observation here is that if you only have a tensor network defined over that slice, that is not enough to compute at least a subset of the observables of interest in the state. So one example of the quantities that we cannot compute are entanglement entropies of subsystems, in particular in the dynamical states. So as you know, when you have a dynamical setting now, it is not enough to use RT, but instead you have to use HRT, where you now extremize the area. Or you can equivalently, you can think of it as in terms of the maximum prescription, where you first fix a slice sigma, find the minimal area, and then you maximize over all possible sigmas. You can find actually an equivalent. You can think of it as find an equivalent version in terms of tensor networks. You can also use maximin. But the important observation here is that in generic time-dependent cases, it is not true that the maximal volume slice can be foliated by HRT surfaces. So in general, HRT surfaces, they lie everywhere inside the will-of-the-width patch. So then it is not true that only with one tensor network defined over the maximal volume slice, it is not true that that is enough to compute a subset of the observables. Then based on that observation, we proposed now that perhaps what you need to do is to consider an ensemble of all possible tensor networks defined over all possible Cauchy slices inside the will-of-the-width patch. And then we can compute complexity as a sum ensemble average. Where here I'm not specifying too much of this proposal, but in order to completely specify it, you have to define the optimized weight functions and measures of integrations to account for, to say what type of slices do you need to consider. And then you have to also define this parameter that I'm just labeling as H bar, but you have to say what is that, no? So we introduce it here, thinking that this is a time scale such that for static cases, then it is valid to use the saddle point approximation, and then the relevant saddle in that case would be given by the maximal volume slice. But in more general cases, you can think of this H bar to be a time scale that characterize the rate of change of your state. We have not tried to make this more concrete, but as a feature, we want to try to connect it with CA, and even with something that is uses quite a similar language, that is the path integral optimization complexity. We're thinking about some other possible outlook. In particular, if there is an analogous of Lorentzian multiflows. So in the Riemannian case, multiflows are a set of flows that were needed to prove the monogamy of mutual information. So we're wondering if there is a Lorentzian analog. And similarly, we're thinking if there is a Lorentzian analog of what is called as hyperthreads. This is a generalization that instead of connecting only two boundary points, you can now encode, at least in the Riemannian case, you can encode multipartite entanglement. We're thinking about going beyond the linear approximation and thinking something about bulk reconstruction, in particular, thinking that these threads can probe even the region near the singularity. Yeah, so that's it. Thanks very much.
So I have a question. Maybe I was just a little confused by the last slide, but you mentioned that in certain cases, you know, that the slice that you should be taking in the bulk is not the minimal, like this last point. And you know, that kind of jives a little bit with this notion that the complexity should be really hard to compute, but if people the volume, which is some, some bit thread formulation of, max flow equals min cut, that's something that admits efficient algorithm. So is there some way of saying like how which which slice is the most relevant one here? Like
no, well,
you might need to consider suboptimal ones. Is this saying that it's a more difficult optimization problem that you have to solve in the bulk?
So we are proposing that now you need to propose a discretize, a way to discretize not only one slice, but you also need to discretize space-time. So this path integral, what is hidden here is well, the weight function and the integration measure. But upon picking optimal functions, then what we are thinking is optimal ways of discretizing space-time instead of only space.
Any further questions? All right, if not, let's thank our speaker. Actually, I see one online from Veronica. You want to go ahead and ask?
Okay, sure. I just wanted to follow up on that last point, which is, I mean, if you have a set of HRT surfaces, of course, they don't lie on a single volume maximizing slice, but they also don't lie on a, pre-optimized set of volume maximizing slices. So it doesn't sound like if you fix any optimal measure that you could still hit all of the entropies.
Exactly. So they are not going to lie on a single slice. That's the point.
But also they don't lie on a, I mean, depending on the region.
Yeah.
I'm saying that even if you try to take a measure over multiple slices, you still would not be able to recycle that same measure for computing all the entropies. That would depend. That would be an extra data that optimum would depend on what regions you would have picked.
Yeah.
So it doesn't sound like you could do it with just one of these optimized distributions.
Yeah. So that's something that definitely we're thinking about. So far, this is not a very concrete proposal, but these are the type of details that we are now thinking about.
Okay.
But yeah.
Virtual questions? All right, let's thank Juan again.